Hello, everyone. Welcome to the Action Forum. My name is Winifred Okafo, and I'll be hosting today's section. I'm thrilled to be here with all of you as we explore some amazing topics and ideas in technology, AI, and innovation. But before we go into today's topic, we have an amazing opportunity for all of those who stay until the end of this call. So sit back, learn, get your questions ready. All right. Today's session would be on teaching cars to drive themselves. But for those who may be new to us, Things in AI is a multi-award winning social impact initiative launched at the United Nations AI for Good Summit in 2018. Our mission is to empower the next generation of AI leaders and innovators. And over the years, we have reached over 35,000 plus young people across 100 countries worldwide, making a global impact. About today's session, in today's session, we would have a lot of things to discuss and we'll be learning about self-driving cars and would also discuss the challenges we face in the industry. After that, we'll host a short feedback session and a question and answer basically. So basically listen, jot down things just in case you have any questions, you'd have a chance to ask at the end of the session. And over to our speaker, I'm delighted to introduce our speaker for today, David Cook, a lead engineer at Wave. Oh, yes. I'm super excited. I get to host this because this means I get to learn a lot as well. David is a software engineer who learned how to program as a teenager because he wanted to make games. Now he builds software to help other developers build products, and in his free time, he still follows his passion of creating games. And we thank God he's also using his free time to give us amazing talk. So let's give a warm welcome to David and let us begin. David, over to you.
Nice. Thank you very much. Yeah, I'm excited to chat with everyone here. If I go ahead and take over sharing the screen, thank you. Cool. Yeah. Hello, everyone. Thank you very much for coming to watch me talk about AI. I don't know. It's a cool thing to get to do this. I've been a fan of software and building software for a long time, and it's really cool to know that I get to work on such interesting things. Y'all see the screen all right here? My presentation all right here? So good. Cool. Cool. Yeah, I am a software engineer. I've been programming since I was 13. And was said I got into programming because I wanted to work on video games, which I really recommend for anyone who wants to get into programming. Learning to make games is a really worthwhile thing. It teaches you about a lot of different disciplines of software and is just fun as well. Right now, I'm a DevOps engineer, which basically just means that I build the tools for other software engineers to develop the software at my company. So like if all the software engineers at my company were carpenters, I'm basically the one setting up the workshop, which is fun because there's a lot of interesting challenges there. And you know then that the work that you're doing helps everyone else enjoy their jobs more and get more done. For the past 2.5 years, I've been working on self-driving cars at a company called Wave out here in London. That's a picture of me and my mom. Believe it or not, I'm the one on the right. But it's cool. It's been interesting and fun. So today I'm going to be talking a bit about what it is that Wave is doing and how we're approaching sort of self-driving cars, how we teach cars to drive, and then sort of like the major challenges that we're facing in the industry, both with self-driving cars and with AI more widely. So yeah, Wave, we are working on self-driving car AI. So we're not trying to like make a car. We are instead trying to make the AI that can drive a car and then work with other companies to get that deployed. So we've got deals with Nissan and Stellantis to make self-driving cars with them and put our software into those cars, and with Uber here in London and hopefully elsewhere in the coming couple years. Should be pretty cool. So yeah, how do you go about teaching a car to drive? Well, there's some core problems here. First off, you need to be able to perceive the world, to be able to make decisions about how you're going to be driving. A good first step is to be able to understand the world around you. Are there cars around you? Are there pedestrians, buildings, things to hit or that you shouldn't hit, markings on the roads, road signs, all kinds of different things that you have to perceive, and you have to get it right when you're trying to figure out what you're looking at. You also have to do this quickly. If you're only able to make a decision, perceive the world, and decide what is around you once per second, if you're driving 5 miles an hour, fine. That's not great, but that's fine. If you're driving 50 miles an hour, you are traveling a very far distance, and a lot of things can happen in that second. So you have to not only perceive the world accurately, but you also have to do it very quickly. And then also you have to make a lot of decisions to make sure that you are driving safely. And not only do you have to be driving safely, a big challenge as well is that you have to, as the person handing control over to the computer, not only do you have to know, not only does the computer have to drive safely, you as a person have to be able to trust that it's driving safely. So the computer driving the car has to be predictable with its decision making, and it also has to be able to handle edge cases. I mean, if you're driving around, like, all kinds of things can happen. Roads are not clean, isolated environments. There's construction going on. There are people who are crossing not at crosswalks. There are other drivers who have forgotten that they need to make a turn right in front of you, and they cut right in front of you. Cyclists, all kinds of things that you have to deal with. And it's really, really hard. I didn't know about this before joining Wave. One of my coworkers shared this last year, that it was the 30-year anniversary of this project called the No Hands Across America tour, where some researchers from Carnegie Mellon, they worked with a number of different groups to put together a self-driving minivan back in 1995 and put computers in the back of it. And it was able to drive across 98% of the United States back in 1995. I was 4 years old then. I'm 34 now, and we're still continuing to work on this. So, like, self-driving in good situations is not really the hard part here. The hard part is that final 2%. Why is it that we were able to drive 98% of the way across the United States back in 1995, and we still have a whole bunch of different companies putting a lot of effort into figuring out that final 2%? It's hard, and there are a few different ways that people have been approaching this. You might have seen Waymo before. Depending on where you live, you might have seen them driving around your cities. They're in a number of places in the States, and they're just now coming to London as well. They take a hybrid approach where basically they have a lot of sensors on their car that looks around at the environment and figures out what is around it. They use AI to classify the objects. They build up an internal map of what the world is around them, and then they have rules that they've defined to make it drive around. This is oftentimes going to be things like, if there's a red light, brake. If there's another car coming at us, drive to avoid it. Rules around getting onto on-ramps, off-ramps, handling pedestrians, all kinds of things. But you have to program in each one of those rules. So if you encounter a scenario that you don't have a rule for, the car is going to struggle with that scenario. And the advantage here is that it's easier to get it on the road initially. My understanding of the way that Waymos work is that they're good drivers. I've been in them a number of times, and like they're very solid drivers. Their approach is working quite well. So they're able to handle that like 98%, probably more like 99%, quite reliably. But the thing that they're really, really good at is identifying situations where their AI is not able to handle it. And then they have a control room where people sitting at computers can place waypoints for the car to drive through when it encounters a situation that it doesn't know how to handle, which is a pretty good way of approaching solving that final 2%. You keep having the AI try to resolve it and then call home when it's not able to. The way that we're approaching it is, it's taken us longer to get onto the road, but it's a bit more generalizable, where we just take in data from the sensors. We have a very sophisticated machine learning neural network that sits in between the data that's coming in and the steering decisions that are going out. So we just take in a bunch of data, take in a bunch of sensors, look at cameras, radar, LiDAR, or whatever, and then output driving decisions, which ends up being much, much better at generalizing. But the challenge is there that you need more data. And then it's also a bit more challenging to validate that it is going to reliably be making good decisions in novel situations, which is something that we've put a lot of effort into. It's important to be safe when you are driving a 2-ton robot around cities. It's important. So, like with this Waymo approach, they strictly define a bunch of the different rules for the behavior of the car. With our AI and with a lot of modern AI, I mean, this is the case for, large language models and other types of AI that exist. A lot of it is just sort of growing an AI. You set up an environment in which the AI can learn, and then you give it a bunch of different examples and you give it a bunch of different scenarios that it can learn from, and you just sort of grow the AI. So our approach to it, and this is a pretty common approach generally, something called imitation learning or behavior cloning, where basically you just get a load of examples of people doing the thing that you want the AI to do, and you train the AI to copy the actions that the humans are taking. This requires quite a bit of data. Ideally, you want driving from as many different scenarios as possible, and you take video or other sensor inputs from the person driving, excuse me, and then record the outputs and the decisions that they're making, and you keep training the AI until it is reliably taking the same actions that humans take. And this gets you most of the way there for a lot of different scenarios for self-driving, and then also of other AI applications. Behavior cloning imitation learning is a pretty thing. This is a large part of how large language models work. Basically just trained to predict the next word in text they've got. And you do a similar thing in self-driving cars. Then to the rest of those situations, it might turn out that in your imitation learning, behavior cloning, it's able to handle most situations, but you identify that there are some situations that it's not reliably able to handle. You record those situations. Something happens where one of our vehicle safety operators needs to take over. Usually we'll want to understand what it was that happened and record that scenario and make sure that the AI doesn't do that same thing that would have been dangerous or otherwise something that we don't want the car to be doing, and then try to learn from that. We take the recording of that scenario and create a virtual playground for the car or for the AI to be driving a simulated car in. And I've got videos of that coming up and just a slide or two here. And it ends up being pretty effective, a very cool sort of way to teach the AI drive and to give it an environment in which it can learn. And I think about making a self-driving car, any of these large companies that are putting together sophisticated AI or sophisticated software. To me, one of the most interesting things is how quantity and scope of people that you need to be able to put this together, right? You're not just making AI that can drive a car. You're building the whole environment in which an AI can learn to drive a car and building tools to assist others with understanding what training methods or data or anything else is relevant, in addition to having people that are working on building the actual machine learning algorithm. You're also having people build these types of things right here, the simulators, where we reproduce mistakes that the agent makes. So you can see here, this is actually in simulation. Just back this up. So what you're going to see here is on the right side, you'll see some flickering, people moving around. That's because this is from us actually driving down a street in London, capturing all of those camera footage and then reproducing this in a virtual world, so that then what we can do is make sure that so at one point there was a car, one of our cars was driving down the street, the AI was controlling it, and it made a minor mistake. The vehicle safety operator took over and recorded that as a scenario that happened where the AI made a mistake. So first we make sure that the AI will reproduce that behavior, that it will make that same mistake. So what we're looking for here, there are going to be some lines at the bottom. One of them represents the speed of the car in real life, and then the other one is the speed of the car in this virtual world. So we want to make sure that those lines line up to first make sure that our simulation of the car matches what happened in the real world, so that we know that our simulation is an accurate depiction of the real world. So you can see here the car is going to slow down, and it shouldn't have slowed down here. You can see that the red line deviates away from the green line because in reality, in real life, a human took over here and sped it back up because there was no reason to slow down here. So this was a mistake. Now we want to have the AI learn from this mistake. So one of our engineers will go in and have an idea about how we can train the AI to avoid this in the future. And then in simulation, we can make sure that we've learned from the mistake. So what we're looking for here is the line just stays flat and that the car doesn't slow down going through this intersection. And boom, just like that, We know that we have solved that issue with this version of the AI. And so what you do is then build up a huge corpus, a huge data set of tons of different examples of cars driving in different scenarios, and make sure that when we are developing the AI, not only has it learned from these mistakes, but also we're giving it an environment which it can experiment and try out new things, learn from these mistakes. So then from there, we want to do this a lot. You want to get as much data as you can, because you want to teach it as much about the world as you can and have it be able to generalize as much as it can. We've got cars driving all over the world now, collecting data and giving us tons of different scenarios to learn from, different weather scenarios, traffic, time of day. You can see here we're actually driving through the Italian countryside on some dirt roads. And yeah, just trying to get as much data as we can so that we have as many examples as we can to learn from. And this ends up being pretty cool. This scenario here, we didn't train the car to drive on these Italian streets. This is the advantage of one of the really cool things, I think, with this sort of like generalization of understanding, is that we can introduce it to a new scenario and it's able to handle those scenarios. I don't know, just getting to be a part of a group that's building stuff like this it's cool. Very interesting. It's interesting stuff to work on. But then the challenge becomes, once you've collected a lot of data, if you've got loads and loads of video and different scenarios that you're training on, you got to select what things you want to be learning from. The more data that you have, the longer it takes to learn from it. And additionally, if you drive down the same road over and over and over and over and over and over, how many times do you need to actually use that data to learn from it versus biasing yourself to just being really good driving down that one road? Because the data that you have affects behavior. This is actually a picture that I took while I was on a road trip a few years ago, driving through the Midwest in the States. And it's, if you live in the Midwest in the US, you know that you probably shouldn't go on the road during the first snowstorm, because oftentimes people who are not familiar with driving on snow will make mistakes. I probably, on this road trip, this was right after the first snow of the season, I probably saw 10, 18 wheelers that had come off the highway. And it's people being unfamiliar with driving in the snow and the precautions that you need to take. AI suffers from similar sorts of things. If you've never seen snow before, you're going to have a tough time driving in snow. And similarly, if you are like, if the only scenario you've ever seen is rain, if it starts being sunny out, you have to start dealing with glares and you have to start worrying about these sorts of different things, and need to be trained in as many different scenarios as possible. But you also need to make sure that you don't overfit for it. If you've only driven in snow, then you're going to struggle once you get onto just plain pavement. So it is a really complex process of identifying right pieces of data that you need to use to train the AI to be generalized in the right ways. How do you decide on that? Well, it's science. You come up with a hypothesis how you can better train the AI, what is going to be better data sets to work. You can change the order of the data that you're training on, adjust the metadata around it, how you're changing training methods, whether they should be using reinforcement, or all kinds of different things. This is the large part of machine learning research. You have a lot of people who are just after experiment, and a lot of them end up working. But that's the whole thing, is that you are science, and a lot of science experiments the value that you get out of those things that don't work, then what doesn't work, that helps you then identify what does, what data is going to be relevant. So for example, let's say that you think that you can do roundabouts better than we're currently doing roundabouts. You might come up with this hypothesis for how we can better train the AI to do roundabouts. You send that off to simulation and you wait for a day for all the processing to go on and to validate that your changes are good. Cool. It has made roundabouts better in simulation, and it has not made the car more dangerous. So let's send it out to the road and see if it works. So this is actually our car driving on the Magic Roundabout out in Swindon, which is one of the more complex traffic situations that you can be in. Yeah, so we basically just tell it to drive from one end of the roundabout to the other, or give it a route that involves coming through the roundabout. And look at this. Fantastic. Your experiment has gone well. And then you just integrate your changes into the rest of the training processes. And that's sort of how a lot of modern AI is developed these days. Is you are integrating your changes. You're gradually developing the process by which you select the data and by which you train your AI and collaborate and work together to put together these systems for basically growing your AI. So then one of the challenges as well is that the better that you are at driving, the harder it gets to know that a change that you've made has made the car better. For example, if every kilometer that you drive, for every kilometer that the AI drives, if you have to take over 10 times, you really don't need to drive that far to see that it has gotten better. If I make some change that ends up making it safer, I can drive just a couple of kilometers and then be confident that it is going to drive better and faster, or more reliably. Again, one intervention per kilometer. The amount that you have to drive goes up, but still pretty feasible. 0.1 interventions, you're really going to need to do a lot of driving. And then also the situations in which you're running into issues become more and more and more sort of edge cases that you have to deal with. And it becomes more time consuming. And some of those situations that you are having trouble with might be dangerous to reproduce in the real world. And then as you get lower and lower, the amount of data that you need to validate that your changes have led to improvements becomes harder and harder. So how do you get those edge cases? You can create them in simulation. So this is from, we've got an article that we published about using generative AI to generate scenarios. So you take past data and then you do things like this, where this is not a real thing that happened. This is just based on past data of us seeing trucks and driving around corners. And we can create fake scenarios of dangerous situations and make sure that the car doesn't crash in those situations. We can do that for a wide variety of scenarios, any weather, traffic patterns, lots of different situations. And we need a lot of those, and they need to be realistic as well. So we have the technology to generate these. We have the technology to simulate them. But then it starts to become this issue of how helpful are the synthetic training data? How helpful is the data that the AI has created for training you about the real world? Is the data that the AI is generating representative of the real world? And then as well, how do you know that the car, when it's making decisions, is making the right decisions? If you're constructing a bunch of synthetic scenarios, if you're constructing a bunch of fake scenarios, you have to really decide how are we going to be evaluating that the car has done something right or done something wrong? And this is a problem throughout all kinds of AI. For large language models, you run into the problem of evaluating the output of a large language model. Like, a lot of the companies just use people giving thumbs up or thumbs down, but that doesn't qualify for that. That doesn't lead you to end up with high quality output. It leads you to end up with output that people like. And there's no really objective way to measure, is a poem good, or like, was a summary accurate? These are hard things to measure. Image generators as well. Is the face uncanny? Is this a real animal? Was the chatbot support helpful? And, did we give the bus enough room to get around the corner? You can do some geometry and measure that, but sometimes it can be hard to measure that sort of thing. Or was it a comfortable ride? You can measure and estimate G forces. But generally speaking, for a lot of these different scenarios, it's challenging to set up not only automated generation of these different scenarios, but then automated validation of these scenarios. So a lot of the challenges with AI these days, most generally, is not necessarily how do we teach an AI to do something? In large part, it is, how do we teach the AI to do a thing well? And how do we know that it is doing that thing well, reliably, and in as many scenarios as we can? And this is not a presentation where I'm going to come out and say, here's how you do it, because we don't know. We have a lot of different methods by which for our cars, we have a lot of different methods by which we are really, really evaluating the safety of it. And they are quite good. But for basically all AI, the challenge of validating that it is making the right choices in all scenarios is sort of the core problem here, and one of the really interesting problems to address going forward. It ends up being this thing of like, are we going to be able to find a generalized solution to determining whether or not AI are making good choices? If so, that opens up a lot of possibilities for where AI can go. But I think that's quite unlikely. And generally speaking, a lot of this ends up just sort of being smart people building the tools to enable us to evaluate AI behavior. And yeah, it leads to getting to work on some interesting things and deal with some interesting challenges. And that is the end of my slides that I've got prepared. Ooh, cool.
Thank you so much, David.
Thank
Thank
you.
you. This was very insightful. We have a lot of questions waiting for you, and I will just take them. I'll just take a one after the other. I think the first question says, what about NCCL? Is it necessary in this scenario?
I am not familiar with NCCL. If that's the NVIDIA Collective Communications Library, I just Googled it. I'm not too sure. If you could clarify what NCCL is, that would be cool.
Okay, I'm guessing, please clarify what NCCL means.
Oh, non-centralized compute.
Non-centralized,
Oh,
yeah.
I am not too sure. That is cool.
Okay.
I'm going to have to look that up.
All right, so why that is happening? The second question says, how do you guys filter the data which is actually needed?
There are it is largely just people who are quite familiar with machine learning who are just making their best educated judgment calls on what data is going to be useful. And then will you'll run an experiment where you try training the AI on that subset of data that you think is useful and see whether or not it did better. It really is a lot of there's some advanced techniques that you can use for identifying what data is going to be useful, but a lot of it is experiments and trial and error.
Okay, thank you. Thank you so much. Next question is, tools like Mesa does not work with this kind of simulation, right? So the person is asking if Mesa works for simulation.
Yeah. The challenges here, yeah, it is interesting as you get into it's interesting as you get into more sort of like domain specialized AI challenges that it ends up being a thing that you oftentimes end up having to you hit an upper limit with the publicly available tools, and you need to oftentimes start cooking up your own sort of tools. The underlying core sort of like libraries for defining neural networks and whatnot oftentimes remain pretty similar. But in terms of building environments for running simulations or evaluating the quality of the AI, you a lot of the off-the-shelf stuff you just hit a limit with after enough time. And then as well, sorry, to go back and answer the previous question a little bit in more detail, filtering the data which is actually needed. There is a cool technique in like developing AI called ablation studies, which is where you have an AI, you have a model that you've trained that is doing quite well, that has led to a pretty good result. And then really important is that you need to challenge your assumptions about what it was that led to that good result. So you then systematically, let's say that you have a big data set of stopping at stop signs or something like that, and you want to be sure that your car's ability to stop in the right places is related to having that data set of stop signs. You take out that whole data set of stopping at stop signs, you run the training on it, and then you see how the car does in that same scenario to identify whether or not, yes or no, that data was relevant to the situation. Of course, in a situation like with stop signs, it's probably good to have the data there, but you can take that into more and more sort of like granular scenarios. Yeah.
Okay, thank you. The fourth question is, when training across drastically different cities, like raining, left-hand drive London versus sunny, right-hand drive California, how do you ensure the model generalizes smoothly without overcorrecting or forgetting its previous safe habits?
Yeah, that is hard. It's hard. You start off with making sure in simulation as much as possible that it's going to be doing the right things. But then, I mean, really, for the most part, you do just kind of have to hit the road and see. Anytime that we are putting our cars out into the physical world, we have highly trained safety operators that are ready to take over. And always, I mean, it is fascinating to go for rides with them sometimes, because you will realize how little you know about the laws of driving on the road. And especially as an American being over here in the UK, how little I know about the driving laws here. And so, yeah, it ends up being this thing that to make sure that we are generalizing correctly, it again just sort of comes down to having some people who have a hypothesis about how they make sure that the AI is generalized, and then testing that out in simulation and then testing it out in the real world. And that's where these sort of ensuring that we are not overfitting type thing and ensuring that we are generalizing correctly. If you start identifying that you're driving quite well in one city versus another, that will lead you to adjusting the data that you're training on.
Okay, I hope that answers the person's question. All right, we have another question that says, when using generative AI to stimulate dangerous edge cases, how do you prevent the autonomous vehicle from accidentally, I can't see what the person wrote, but basically, how do you prevent it from having like accidents and, physics glitch rather than valid real world hazard?
How do we, when using those dangerous scenarios for training, make sure that it doesn't do those dangerous scenarios type thing? I mean,
Yeah.
it's largely that you in the simulations make sure that it doesn't crash. And if it does, then if you're in training, you give like a negative reward signal and steer the AI away from growing in that direction. And then if it's in validation and it is regularly crashing in those bad scenarios, then you don't let it go out on the road.
Okay. Next question says, I'm sorry, we have a lot of questions for you.
Oh, please,
Everyone is
quite all.
very curious, wants to have answered. So the next one says, Wave 2, 2.0 uses an end-to-end model, which is sensors in and driving out. How do you translate highly subjective human qualities like passengers' comfort or driving courtesies into plain mathematical reward functions for a neutral network?
Yeah, that is a very good question. Turning that into quantitative data, like a quantitative measurement, um, is a challenge. I think a lot of it is the behavior cloning. That's where all of our efforts started off on, and it is pretty good at driving comfortably. And then from there, I mean, the specific approaches for it, I can't necessarily speak to. But you can measure things like G forces, and then you can have potentially different scenarios that you run in simulation where the car drove in an uncomfortable way, and then make sure that it doesn't repeat that. But yeah, I mean, that is the hard part. How do you reliably have the AI deal with how do you reliably have the AI understand when it's doing something comfortable? I was recently in my free time, using an AI to write some software, and I started to have this sort of realization of coalescing of ideas that I've had around this sort of stuff that, as a software engineer, helped make me comfortable about the idea that AI is not going to be taking my job. And it is precisely that thing of the human experience is something that you can't really put into an AI. You know, you can describe it with numbers, you can describe it with words, the scenario that you're in, you can describe it with pictures, but you can have an AI you can have an AI read as many negative reviews about an app online as you want. It won't be able to understand what it's actually like to use a frustrating app. And as a result, you can't really build an automated feedback loop where you tell the AI, make this not frustrating to use because it doesn't know what frustration is. And so to make the car comfortable, a lot of it is still just trial and error and finding good examples of the car driving comfortably.
Okay, thank you. The next question is, since finding rare edge cases in the real world is incredibly slow and expensive, do you think generative stimulation can eventually cover 100% of safety corner cases, or will we always need a physical fleet to validate reality?
I don't know. I think hypothetically, oh boy, hypothetically, you might be able to, but I don't know how much I would ever trust. I don't know. You would need a lot of data to prove that the simulation is trustworthy. Yeah, that's the main thing. How feasible that is, I can't really necessarily speak toward, maybe. But the main thing is you would just really, really, really need to be able to validate that that the simulation is an accurate reproduction of the world. And that things don't change in the world that your simulation hasn't captured. If flying cars start coming out and they're flying like close overhead, does your simulation include those? And will the sensors start behaving weirdly if they start seeing a car overhead? Yeah, there's sorts of situations to deal with.
Yeah. This question speaks personally to you. It says, Dave, you started programming at 13 to make video games, and now you're in the devs. How have your roots in game development coverage with your engineering background to help build a virtual driving
Mm.
playground?
Ooh, interesting. I think that the advantage, I think a big advantage of game development is that you really have to consider a lot of different elements of how software works. You have to consider, the basics of programming logic around what like if else's and for loops and the basics of programming. But then you also have to start considering optimization and how you are going to be designing algorithms to run optimally. You then also are having to work with a bunch of different libraries and a bunch of different pieces of software and file structures and like all of the basics of interacting with a computer on a basic level. Then you're also having to learn how like graphics work and sound work and stuff like that. So it ends up being a good way of getting exposed to a wide variety of things that you can do with a computer. But then additionally, I think quite importantly, it's also fun. And if your goal is to learn to program, I can read some textbooks and I can do some structured courses like for a period of time and on a regular basis for a period of time. But I find that I get really excited and I can let my creative interests and the things that I want to do out when I'm building games and when I'm experimenting with my own projects. And I think that loop of being excited about building something and really pushing yourself to build something complex is important for learning and pushing your capabilities. And then learning to learn, which is a very important element of it as well.
Okay. There's a question here that says, do you have your own wave-made AI system that overtake the publicly available system? As in, if you have outgrown the public versions.
We we build our own AI, and I mean I think it's better than what is publicly available. Yeah, it's pretty good. I think it's pretty. I've been in the car. It's pretty good.
Hey, so someone says, who is responsible when it gets wrong? Like if a self-driving car makes a mistake, who's accountable for it? And how do you build trust with people who are nervous about this technology?
For as to who around like legal responsibility, that comes down to a variety of different factors that I can't really necessarily speak to. How do we build trust? I mean, it really is just by making sure that the car is good and reliable to be around, and that people that you give people reasons to trust it, and that it's reliable and it's predictable and it's safe. And I cycle to work every day, and my the cycling paths in London, some of them are good, some of them you're driving right next to another car, and it happens pretty decently often that I will be riding my bike next to a driver who is doing unsafe things. Whenever I ride my bike next to our car, which when I get close to the office, it's not uncommon for me to be riding my bike and see one of our cars nearby. And whenever I'm riding my bike near our car, I feel very safe because it's really predictable. It gives me plenty of space. It's never in a rush. It's never impatient or angry or has had a tough day at work or anything or is tired. It's just a computer that is genuinely at its best. It's a really boring and safe driver. And I think that's how you do it.
Okay. So what would you say is your, like the hardest problem you still haven't cracked? Like what's one situation on the road that's still really difficult for self-driving cars to handle? And why is it so tricky?
I have a number of coworkers uh from I have a number of coworkers from, India and from Rome and from a number of other places where the laws of the road are not as strictly followed. And my coworkers will regularly talk about how excited they are to see how our car handles those sorts of situations because it, yeah. I mean, if people aren't following, it's just sort of like unpredictable situations tend to be interesting. As for like specific scenarios that we're struggling with, I'm not too sure. It ends up like we're pretty good at most scenarios, and I can't really speak to any specific ones that we're struggling with.
Okay. I think this would be my last question. But okay, before I take my last question, someone has a question. And it says, will they be coming to Africa anytime soon?
I am not sure. I hope so. I hope so. I'm not sure. I know we did an around the world tour, and we might have driven through Africa, but I hope so. I want it all over the place.
All right, we're hoping to get that feedback soon. Would we need something like that in Africa?
Yeah.
All right. So let me ask you my last question. This one is coming from me personally.
Hmm.
I'd like to know if you have, okay, apart from your work in Wave, I know you said you like, building games. Do you have any demo for us? Is that something you're currently working on? Is that something for us to look out for? Because I'm truly interested in this.
Yeah, I have. So I think I've been interested in machine learning and like reinforcement learning specifically for over a decade now. So even though I don't work directly on it at the company, I've been working on hold on, let me unblur my camera. Background, turn off the blur. Cool. So this right here, for anyone that is stuck around, this I think is pretty neat. I have been working on a thing to do reinforcement learning to teach an AI to play Mario Kart. So let me make my camera a little bit smaller here. But you can see here that this is after 100,000 steps of training. So this is probably after 2 or 3 real world hours of playing. It's learning to play Mario Kart here. And I think that
Mhm.
it's pretty neat. It's just taking in what the AI sees is this right here. So this little box of color graphics coming in, and then what it outputs is the buttons on a Game Boy, and it's gradually learning to play. And over here on the right, I have like a visualization of the vision neural network that it has. So over time, the places where it's lighting up here, let me see if I can zoom that in a little bit. The places where it is lighting up here are places that it is sort of looking at or focusing on. And so over time, this will gradually start to turn into it identifying different features, like where is the road for it to drive on, or where are hazards, or other things like that. So yeah, it's been a neat little project. Interesting. What would be your recommended path to someday work on this type of project in the future? To like work on AI? I mean, truly, like studying machine learning, there are a number of good books on machine learning out there. Understanding the underlying mathematics behind it is important for understanding how you can use numbers to represent other information. The fundamental mechanics of how that works is really, really important for understanding how neural networks work and how AI works. So I would say truly just like experimenting with different ideas and pushing yourself to try out different elements of machine learning. There's a lot of stuff out there. There's a lot more than when I was coming up and learning how to make games and stuff. And yeah, just finding good books and articles on learning the machine learning, forcing yourself to do the hard stuff and figure out how the underlying mathematics of it work. And then from there, just experimenting with different projects and finding things that you find interesting and want to push yourself on.
All right. Thank you, Dave. This was such a wonderful session. We definitely learned a lot, and that's why we had a lot of questions to ask. Thank you so much.
Yeah, my pleasure.
And
Thank you.
thank you, thank you. Before we wrap up, I would like to share some amazing opportunities for everyone to continue their learning journey with things in AI. So, as a special thank you for being here today, like I promised you earlier, would love to see you return. So, join us in August 10th to 14th for our AI for Good incubator. It's a 5 days bootcamp style program. And because you're here, we have an alumni discount for you. So, use the code AI for Good, so AI for the alumni for your individual spots. We also have a grab 4 tickets at once. So if you want to buy 4 tickets, the first one is automatically on us at checkpoint. So which is just like buy three, get one free. So you can use the QR code on the screen to scan and make your purchases. And if you're 16 and older, do well to join our alumni community on LinkedIn with the QR code you can see on your screen. That's where you get first-hand information on our programs and event coming up, and also discount codes like this. And lastly, join our next action forum on Thursday, the 23rd of July, 2026. On this action forum, we would explore how to look past generic chat box and design AI that solves real world problems. So you would discover the secret of human-centered designs, the challenge of beating the AI hype. So what's creating truly useful tech actually means for the future of innovation with our special speaker, Calypso Rose. So we definitely want to see you there to learn. That's a month from now, Thursday, 23rd of July. Please scan the QR code and register. Don't forget, our mission is to empower the next generation of responsible AI leaders and innovators, and we need your passion and creativity to make that vision a reality. So stay curious, keep learning, and remember that the future is in your hands. Goodbye. Thank you again for your energy and participation. We look forward to seeing you on Thursday, the 23rd of July, 2026, and all our future events, workshop, and our global Things in AI community. Until then, stay innovative and have a wonderful day. Goodbye, everyone.